Welcome to solverfy.
We're asked to prove that there is a unique minimum spanning tree in a connected weighted graph if the weights of the edges are all distinct. To do this, I'll use a proof by contradiction. So let G be a connected weighted graph with n vertices. Let T be a minimum spanning tree of G. Which we know exists by either Kruskal's or Prim's algorithm. And suppose that the weights of the edges in G are all different. Now, for the contradiction, we're going to suppose U is a different minimum spanning tree for G, so it's different from T. Then, since they're both minimum spanning trees, it follows like the same weight, and so we're going to suppose that the total weight of T equals the total weight of U, which is equal to A Now, since T and U are different trees, it follows that there exists an edge in T but not in U. So find an edge E with vertices U and V in T, but not in the graph U. Now add E to U. Follows that the resulting graph will have a circuit and now, since there was no circuit in T, it follows that there's an edge F that is not in T, but is present in the circuit in U. So you can find an edge F with vertices W and X in the circuit in U and not in the graph T. Now, since the weights of all the edges in G are different, it follows that E and F have different weights. So we're going to assume, without loss of generality, that the weight of F is less than the weight of edge E. And of course, if this is not the case, we could just apply the rest of the proof to U instead of to T. So if we remove the edge E from T and add the edge F to T, then the new tree is still a spanning tree. With the total weight less than the total weight of T, because the weight of F is less than the weight of E. And this, of course, is a contradiction. Since T was supposed to be the minimum spanning tree, therefore it follows that T is the unique minimum spanning tree of G.